So to do that, we have to use this machine. This is called a Geiger-Müller counter. And what this will do, this will tell you exactly how much radiation a particular material is releasing. So for example, what you would do is this. So imagine we have these radioactive rocks. You take your Geiger-Müller counter, you measure it, and it will tell you the radiation, and it will tell it to you in units of becquerel. So becquerels, 1 becquerel means 1 decay is happening per second. If you have 100 becquerels, that means there are 100 decays happening per second. So decay means radioactive decay. Again, this one therefore is more radioactive. So again, it will say to you the becquerels. Now, we know that over time, as the atoms decay, the remaining number of radioactive particles will begin to reduce. So initially, you might have a lot of radioactive particles. However, over time, those radioactive nuclei will begin to reduce as they decay and stabilize. So a half-life is the time it takes for the amount of radiation to half. So, and again, that's measured in becquerels. So half-life, the amount of time it takes for the half of the radioactive nuclei to decay, or you can say for the radiation to half. Okay, I think it's better to use this definition, but just to make sure you understand what it means. So with half-lives, they can also always give you calculation questions. For example, here they'll say to you, look, a particle or a substance has 192 becquerels initially. The half-life is 20 minutes. So that means every 20 minutes, that number is halving. How much would you have after 2 hours? Now, to answer this question, we're going to use the following formula. Number of becquerels at the start divided by 2 to the power of h is equal to number of becquerels at the end. So at the start, how many do we have? We have 192 becquerels. 192 becquerels. Now we're going to divide it by 2, and the reason we divide it by 2 is because, of course, it's halving. Now, how many times? What is h? H is total time divided by time for a half-life. So in this scenario, the total time was 2 hours. Let's convert that into minutes first. So that's 120 minutes. So we're going to do 120, which is total, divided by the time for one half-life, which is 20 minutes. So 120 divided by 20 gives you 6. So we're going to do 192 divided by 2 to the power of 6, and that should give you 3 becquerels. So if you leave this material and for 2 hours, after 2 hours later, you'll have 3 becquerels of radioactivity. So that's one way to work out half-life. Another way is by using the graph. So they could give you this graph and say work out half-life using the graph. So what you do is you go to where time is 0 and you work out radiation. So right now it's 800. Then you half it. So 800, half of that is 400. So then you go to 400 and you see that where that goes up to. So that is at 2 hours. So that shows us that the half-life is 2 hours. Now we can do that again by halving this. So from 800, halving it to 200. Again, go to the time and you should see there. So from 400 to 200, it took again another 2 hours. So that again, that proves that the half-life is 2 hours. One more time, 200 to 100, 6. Okay, so there you go. You can prove half-life using a graph as well. Okay, now, when you if you notice over here, the graph will actually never hit 0, and the reason it will never hit 0 is because although you're measuring the material, the radioactivity using a Geiger-Müller tube, there's always background radiation which comes into the machine, and that's the reason why it will never go to 0. Now, where does background radiation come from? So there are 3 main places. Number 1, cosmic, so from the solar system, from stars and galaxies far away. Also from nuclear waste products, so if people use nuclear power machines or nuclear weapons, and also from radioactive rocks in mountains. So for example, people who have jobs where they have to, like, let's say pilots are at a greater risk of background radiation than people who are on the earth, like on the ground. A nuclear fallout or scientists that work in nuclear factories, again, are at more risk of background radiation than people who don't. Now, there are 2 types of words that you need to know about radiation. One is irradiation, and the second one is contamination. So irradiation is when the object is near you, but it's not touching you. So the radioactive stuff it's just radiating onto you, but it's not actually part of your body. So how you can stop that is by putting the material in lead boxes, using barriers, or remotely controlled arms to operate machinery. And this will keep it as far away from you as possible. Now with irradiation, remember, the most dangerous ones are beta and gamma. So you don't want radiation to in the form of beta and gamma. If it's alpha, that's not a problem because alpha is not very penetrating. So it can come to your body and nothing will happen to you. But beta and gamma are more penetrating, so they can enter your body. Contamination is when the radioactive atoms are on the object or in the person. So if someone inhales radioactive substances, that is dangerous. So how can you prevent that? Wear suits, wear gloves, and use tongs when you're holding stuff so it doesn't go under your nails. Now, with this one, you want to make sure you avoid alpha particles. So if you get contaminated, you don't want alpha particles to go into your body because they are very ionizing, which means they can damage your cells and it can cause cancer. So it can damage your DNA and that can lead to cancer. If it's beta or gamma that's gone inside your body, that's not a problem because they can easily escape because they're very penetrating. Hey guys, if that video helped you, support our channel by liking, subscribing, and sharing it with your friends. And more importantly, if you still have questions, drop a post on our forum at examqa.com, where I will personally be there to help answer your questions. Mohammed signing out.